Hello, today we're going to be talking about partial pressures. Um, and we're going to work a couple of problems with partial pressures. Hopefully it'll be helpful to you if you still haven't quite understood or figured out how partial pressures work. So first we want to take a look at this problem. Let's say we have two separate containers. Each have a certain amount of gas in them. In this particular case, we have 12 liters of oxygen at 1.5 atmospheres, and then we have 8 liters of nitrogen at 0.75 atmospheres. Let's say we were able to basically just open up this barrier in between the two and allow all this to mix together. So what would the new pressure be? So what would our new total pressure be in this particular case? So we can use this concept of the total pressure is going to equal the partial pressure of the one gas plus the partial pressure of the other gas. But how do we figure out what the new partial pressure is going to be? The easiest way to tackle this is to work each of the individual problems as if the other gas were not there. For example, now that we've opened this up, my oxygen once only had 12 liters to move around in. Now it has 20 liters to move around in. So the partial pressure, or the pressure of the oxygen, will actually get lower because it has more volume to move around in. And we can figure out what that will be just by using our standard PV, P1, V1 over T1 equals P2, V2 over T2. So if we assume that we're at constant temperature, we can mark that out, and we can just use the P1, V1 equals P2, V2, and we can solve each one individually. So let's start with oxygen, and my initial pressure of my oxygen is 1.5 atmospheres, and my initial volume is 12 liters. 12 liters. Okay, my final pressure is what we don't know. So I'll actually write that as P2. And my final volume would be the entire container now that we've broken down this wall. So it would be 20 liters. And if I do that math, then P2 equals 0.90 atmospheres. And that would be the partial pressure of O2. Now at the same time, I can also do the same thing for my nitrogen gas. It's starting out at 0.75 atmospheres. And of course it was originally in 8 liters. But then, we don't know P2, but then we opened it up, so now it has a grand total of 20 liters available to move. So we can once again solve for P2, and in this case, P2 equals 0.30 atmospheres. All right. And that would also be the partial pressure of your nitrogen. So now that I have the partial pressure of each individual one, I can just add those two together and say total pressure equals the pressure of my oxygen plus the pressure of my nitrogen. And that's going to be 1.2 plus 0.30. Whoops. Getting ahead of myself. 0.90 plus 0.30. It's going to be a total of 1.2 atmospheres. Now, once you do this, let's do kind of a common sense check. So you had 1.5 atmospheres on this side. You had 0.75 atmospheres on this side. So if you think about it logically, if you opened up the two containers and mixed these two, you would expect the new pressure to be somewhere in between the two of these. So 1.2 atmosphere does seem like it's a reasonable answer based on the original pressures that you started with. If you get a pressure that's less than 0.75 or one that's more than 1.5, then you can be pretty much assured that you've made a mistake somewhere. You should get a pressure somewhere in the middle of the pressures of the individual gases that you started with. All right, let's go ahead and work another problem. Why we're doing this, so you can see a little bit of a different take on the way partial pressures work. And this time we're going to look at if we have, say, 50 grams of methane, CH4, and we also have 50 grams of oxygen at standard temperature and pressure. So we can ask a couple different questions. One is, what would the volume be? And what would be the partial pressure of each gas? Okay, first of all, to get our volume, the first thing we need to do is we really can't work with grams in these types of equations. We know that the best relationship between volume and moles, and volume and gas, is the relationship between moles and volume. You can't really use grams to volume, so we need to convert everything to moles. So let's start here with 50 grams of CH4. We take our molar mass of CH4, which is going to be approximately 16, so say 1 mole over 16 grams, and that's going to give us 3.125 moles of CH4. We do the same thing for oxygen. And that will give us 1.563 moles of oxygen. Now, if we add these two together, we'll get a total of 4.688 total. So now that we know our total number of moles of gas and we know we're at standard temperature and pressure, we can use PV equals nRT to calculate what our volume is going to be. So we know our pressure, standard pressure is going to be 1 atmosphere. Volume is what we don't know, 4.688 moles. And R, if we look that up on a table, we need the one that has atmospheres in the units. And then, of course, standard temperature is 0 Celsius or 273 Kelvin. So if I put all that in my calculator and I solve for V, I get V equals 105 liters. Now, there is actually another way to do this one. Since we're at standard temperature and pressure, we know that 1 mole of a gas equals 22.4 liters. So since we know that, we could actually use kind of a shortcut method since we are at standard temperature and pressure, and we can take our total number of moles, 4.688, and we can just basically use this as a conversion like you've done many other times and say 22.4 liters per 1 mole. Moles cancel, and that gives me, well, what do you know, 105 liters. So basically 2 ways to work this problem. Of course, this one only the bottom one only works if you're at standard temperature and pressure. Now, that answers my first question. So let's look at my second question. What are the partial pressures of each individual gas? We know that the partial pressure is related to the mole fraction or percentage of the moles that each individual gas is of the total. So I can write that out. That is basically like if I want to find the partial pressure of oxygen, that's going to be equal to the number of moles of oxygen divided by the total number of moles times the total pressure. And in this case, the total number of moles of oxygen is 1.563. Total number of moles of gas is 4.688. And then my total pressure is 1 atm. So when I multiply that out, I get 0.333 atmospheres. All right, I can also do the same thing for my methane. I can get in this case 3.125 over 4.688. In this case, it's 0.667 atmospheres. If you want to double check your answer, then you can add these two together, and they should equal back to your total, because we know the total is equal to the sum of the partial pressures. And so the sum of my partial pressures equals 1 atmosphere, so it looks like everything is good, and we have solved this one. Hopefully this has been helpful to you, and if you still have any questions, just let me know.